Hey there, science fans! Ever wondered what sound really is? It's all around us, from the chirping of birds to the roar of a rocket. Well, sound is simply vibration. That's right. Tiny back and forth movements create the sounds we hear every day. Imagine a guitar string. When you pluck it, the string starts to vibrate rapidly. These vibrations travel through the air as waves, reaching our ears and letting us hear the musical note. Pretty cool, right? These vibrations need something to travel through, which we call a medium. Air is a common medium for sound, but sound can also travel through water, metal, and even wood. Think about it. When you knock on a door, the vibrations travel through the solid door to the other side, allowing someone to hear your knock. Sound is all about energy traveling in waves, so the next time you hear an awesome sound, remember, it's all thanks to the power of vibrations. Now that we know sound is all about vibrations, let's dive into the fascinating characteristics of sound waves. Just like ocean waves, sound waves have unique properties that determine how we hear them. First up, we have frequency. Frequency tells us how many vibrations happen in 1 second. We measure frequency in hertz or hetz. A high frequency means lots of vibrations per second, resulting in a high-pitched sound, like a whistle. A low frequency means fewer vibrations per second, creating a low-pitched sound, like a bass drum. Next, we have amplitude. Amplitude tells us how much energy a sound wave carries. We experience amplitude as loudness. A high amplitude means a loud sound, like a jet engine. A low amplitude means a quiet sound, like a whisper. Now, let's talk about wavelength. Wavelength is the distance between two peaks of a sound wave. High-frequency sounds have shorter wavelengths, while low-frequency sounds have longer wavelengths. Finally, we have the speed of sound. Sound travels at different speeds depending on the medium, but in general, sound travels much slower than light. Understanding these properties helps us understand how sound works and why we hear different sounds in different ways. So, how are sound waves actually made? Let's explore some cool examples. One way to create sound waves is with a tuning fork. When you strike a tuning fork, its prongs vibrate rapidly. These vibrations create compressions and rarefactions in the surrounding air. Compression happens when air molecules are squeezed together, and rarefaction happens when they spread apart. This pattern of compressions and rarefactions travels outward from the tuning fork as a sound wave. Our vocal cords work in a similar way. When we speak or sing, air from our lungs passes over our vocal cords, causing them to vibrate. These vibrations create sound waves that travel through the air and reach the ears of others. Speakers also use vibrations to create sound. Inside a speaker, there's a cone-shaped diaphragm. When electrical signals reach the speaker, they cause the diaphragm to vibrate. These vibrations create sound waves that we hear as music, speech, or sound effects. From the simple tuning fork to the complex human voice, sound wave creation is a fascinating process. Section 4. Sound's journey through different materials. We've learned that sound needs a medium to travel, but did you know that sound travels differently through various materials? Let's see how sound's journey changes depending on the medium it encounters. When sound travels through air, it causes air molecules to bump into each other, creating a chain reaction that carries the sound wave. This is why we can hear sounds around corners. The sound waves diffract or bend around obstacles. Sound travels even faster through water. This is because water molecules are packed more tightly than air molecules. Think about how well sound travels underwater. Whales communicate over vast distances using sound waves in the ocean. Sound travels the fastest through solids. Because molecules in solids are tightly packed, vibrations transfer energy quickly from one molecule to the next. This is why you can hear a train coming from a distance by putting your ear to the rail. The type of material affects how fast and how far sound travels. Section 5. The speed of sound, not always so speedy. We've talked about how sound travels at different speeds through different materials, but did you know that other factors can affect the speed of sound too? Let's explore how temperature and density play a role in sound's need for speed. Temperature can significantly impact the speed of sound, especially in air. As the temperature increases, air molecules move faster and collide more frequently. This faster movement allows sound waves to travel faster. So, sound travels faster in warmer air and slower in colder air. Density also plays a crucial role. Denser materials, like solids, transmit sound faster than less dense materials, like gases. This is because the molecules are closer together in denser materials, allowing vibrations to travel more efficiently. So the next time you're thinking about the speed of sound, remember that it's not always constant. Temperature and density can significantly impact how fast those sound waves reach your ears.